So it is indeed my pleasure to introduce today's speaker, Grace Bodine, who is a native of Austin, Texas. And being a Texan, she did her undergraduate work at Texas A&M University, which is also my alma mater. I did my doctoral work there. And while she was there, she did an honors thesis related to soil health. And she then presented that work at the World Congress of Soil Science in Scotland a couple of years ago. And then about 2 years ago, she joined our group in pedology and has been doing some very interesting work on iron and manganese oxides in soils. She presented some of her work at the World Soil Classification Workshop in Hokkaido, Japan a year ago. And last year, when she presented some other parts of her work at the Soil Science Society of America meeting in St. Louis, she received first prize for the Wetland Soils Division student presentation, and then went on to receive third place for all of the SSSA student presentations. You know her also because she's been serving you as Vice President and President of Gates. She's also the Vice President of Phi Kappa Phi, and she's finally coming down the home stretch. Today she's going to be presenting some of her interesting work. She doesn't have time to present all of it. But talking about evaluating iron and manganese reduction in soils using IRIS. Yes. So, Grace, we look forward to it.
Thank you, Dr. Ravenhorst, and yes, thank you. And wow, that almost made me kind of emotional. But yes, good afternoon, and thank you for that wonderful introduction. I'm excited to talk to you today about parts of my master's work with iron and manganese reduction in soil using an innovative tool called IRIS. However, I always like to start my presentations off with acknowledgements. So, of course, Dr. Ravenhorst, my PI, as well as other committee members, Dr. Needleman, Dr. Wilmoth. But I want to give a special call out to David Hutch, who's giving you that double thumbs up. He was the undergrad student that worked very closely with me throughout my entire field work and also a lot of my lab work. He ENST graduate in this past May. I think he's still in Italy working as an agronomist. So. Bright future for him as well. But anyways, before we dive into soil reduction, I want to give more context. So when we're thinking about reduction, we're thinking about wetness in our soil, aka wetlands. So wetlands are defined by the presence of three things. They have to have the hydrophytic vegetation, the saturation, that wetland hydrology, and then also hydric soils, aka wetland soils. I know this group is pretty familiar being situated in Maryland, but I just want to make sure we're on the same page here. And we know that these are very valuable ecosystems, and we haven't been treating them very well over human history, but the last 50 years or so, we've done a lot of work, especially in the US, related to conservation, creation, and restoration of our wetlands. But with that being said, how do we actually know that these restorations and creations are successful and they're beneficial? Well, we generally have to measure indicators that are related to that three-pronged definition. And my work focuses on the hydric soils. Hydric soils or wetland soils are the soils that are developed in these wetland saturated conditions, and they have this anaerobic condition that is developed in the upper part. So when you're going out and locating where a hydric soil is, basically you have to find evidence of one, saturation. This is pretty easy. We can use wells and piezometers and things like that. And sometimes you can just see it at the surface. But anaerobic conditions is a little trickier, but generally we can use something called soil morphology. So looking at the different colors and features in the soil. As shown here, wetland soils tend to be a very dark color or a very gray color that's indicative of that saturation. And that built the field indicators of hydric soil. The National Technical Committee for Hydric Soils, along with plenty of researchers, created this list of indicators based off the physical features in the soil that indicate, yes, this is a hydric wetland soil. However, it's not really reliable when you have altered soils. For example, these features develop over a long period of time. They are kind of the accumulation of hundreds to thousands of years of an ecosystem. But when we're looking at creation and restoration, the soils get all mixed up sometimes. And then with restoration, sometimes you have wetland converted to, for example, farmland. And now we're interested in converting it back to a wetland, but the features might still show from that old wetland history. But if we're in a new wetland, we might not be able to distinguish if this is the current formation of these features or relict features. So in our type of restored and created system, it's just not very reliable, but we can use the biogeochemistry of the soil. So we have the redox reactions that occur in the soil, and really in wetlands, I'm focusing a lot on the reduction of the soil and the reduction of the electron acceptors after oxygen is no longer available once we're in this anaerobic state. So here I have the redox ladder. This is kind of like an idealized model of how we move through our electron acceptors based off thermodynamics and the energetic favorability for microorganisms to utilize them. But for my work, we're focusing on the manganese reduction and the iron reduction, because we're using iris films, which stands for the indicator of reduction in soils. These devices first were developed in a dissertation out of Purdue from Jenkins in 2002 and have been used ever since for practitioners to use, but also in research. The National Technical Committee of Hydric Soils, they create their hydric soil technical standard, which lists all the different methods that can be used to determine the presence of hydric soil. And included in that is the iron iris devices. So what are these iris films or devices? So the way we use them, they're these painted PVC films. I meant to bring props, apologies. But basically we have two versions. The original iron version, that's the orange version. It's a paint of basically a mix of ferrihydrite and goethite iron minerals. And then we have the newer version of manganese oxide iris paint that is essentially bernacite as the mineral. But we deploy these in the ground for usually a month-long period. And as the saturation occurs, and if anaerobisis occurs and enough to reduce iron and manganese, we see the stripping of the iris paint off of the films, revealing that white PVC background. So we can get a visual estimate that is the accumulation of the reduction that is occurring for the month-long period. Iron, again, is the one that's approved for the technical standard. This represents more strongly reducing conditions, while manganese represents more moderately reducing conditions. And even though it's representing these moderate reducing conditions and it's not approved in the technical standard yet, there's a lot of interest around it because it occurs at a redox potential similar to that of other biogeochemical processes like denitrification. So soil reduction requires, of course, an anaerobic state. We also need these metal-reducing microorganisms as they're the actors at play here. We also need organic carbon. That's essentially the fuel for these different processes to occur. And the rate and intensity is really dependent upon multiple different factors. There's more than the three I listed, but we're focusing in my work on the duration of the saturation to create these type of environments, the temperature of the soil, as well as the amount of organic carbon. So going into my research and building this project with Dr. Ravenhorst, we had some guiding concepts going into this. First of all, there's been, ever since the creation of the manganese iris film, there was a lot of interest in comparing it to the iron and figuring out its utility. So Dr. Ravenhorst, along with colleagues in 8 different states, looked at the iron versus the manganese iris films in natural wetlands. And they found that manganese is more sensitive in cooler soil temperatures and thus more informative, while iron was kind of inhibited in the cooler conditions, but more sensitive and informative in the warmer soil conditions. So this led us to think about, okay, maybe the manganese is better at capturing early growing season conditions and the iron is missing it. And also maybe this could be really helpful in Maryland in our wetland mitigation sites, because not only are they highly disturbed, but they're still kind of establishing themselves. Maybe they haven't quite gotten to an iron reducing state. And also a lot of the systems tend to experience a lot of seasonal hydrology. So the water tables are at the shallowest in the winter and early spring before leaf out, and then they drop down and dry out into the growing season. So we built our project based off these guiding concepts and wanted to look at iris films in these restored and created sites across the early to kind of mid-growing season. And then we wanted to compare the iron and the manganese reduction and mobilization based off of the relationship to these specific environmental drivers of saturation, soil temperature, and soil organic carbon. The hypothesis leading into it is nothing extremely novel. It's based off years of research, but the fact that all these drivers, as they increase, will increase the amount of iron and manganese reduction as well. We also wanted to look at some of the thresholds that are set for iron iris films, and I'll get into explaining what this exactly means later on, but basically we assumed that we would see very similar temperature-dependent results as Dr. Ravenhorst and his colleagues saw before. Additionally, we wanted to look at how that removal of the iron and manganese kind of corresponds to the hydrology requirement of the technical standard, but I don't go into this a ton in this presentation. So overall, my master's has been split into two major projects. The first one is the Restored Wetlands Field Project, which is going to be the star of the show today. So the other project, I'll give kind of like a quick peek at the very end because it was like my last 6 months of my life and I want to at least address it, but we won't talk about it. But going into the field project, there's David again. So we had 11 sites across Maryland. These were all inland, non-tidal, freshwater restoration sites. And I'm using restoration, a pretty broad umbrella term here. There was kind of some that were more like true restoration, some that were more a little bit more created wetlands. But regardless, the majority of our sites are owned by the Maryland Department of Transportation State Highway Administration, as they're on average required to mitigate 2 acres of wetlands for every 1 acre they negatively impact in their operations. So there's hundreds of these sites across Maryland. These sites are very diverse. They're not uniform to each other at all. The ages vary, the sizes vary, and the locations vary. They are generally grouped into these 3 different areas of Piedmont, Intercoastal Plain, and Outer Coastal Plain. And at each of these sites, we had a single 3 by 3 meter plot. And the reason why we only have 1 plot at each site is because of our objectives. We were not testing to see whether or not these wetlands were properly restored. We were testing the ability of the iris films. So we were using these sites as simply like a vessel, essentially, to study the iris films. But we would have a 1 meter well in the center of our plots, and then we kind of had what we refer to as a nest of iris films, both iron and manganese, 5 each, kind of radially distributed around the well and alternating. And that actually looks like this. So the white little kind of stubs are the tops of iris films, and the dark in the middle is our camo covered wells. So this is a sneak peek of some of our sites. And I also want to make sure everyone kind of realizes that because of these are in restoration or created wetlands, the soils are very mixed up. They're all weird. They've had to deal with a lot of earth moving, so there's also a lot of compaction. Sometimes they bring in a lot of organic rich topsoil. And this leads to issues with like dense layers and perched water tables and just overall increased heterogeneity spatially than what we normally see with even natural soils. And can't be a soil talk without showing soil. So these are some of the profiles that we got from when we were augering out to put the wells in. And for those that are more soil savvy, you can see that some of these profiles are more natural looking and some you can tell are very human impacted. So for the iris films, we had 7 different deployment batches in the spring of 2023. So the first batch went out in the early February. The last batch came out in the early June. And they would be deployed for about a month. And then we would also deploy these every other week. So we had 2 weeks overlapping for every batch. And the reason why we did this is we just kind of want to have a continuous look over the season as we went, and didn't want there to be a kind of like a break potentially when we deployed our films. But you always deploy a nest, so we always deployed 5 iron and 5 manganese at every batch. So in total, across 11 sites and 7 batches, that's 770 films that were deployed and analyzed. Yeah, so the Now we're going to start going to kind of more data collection and results, but first I'm going to focus in on this kind of environmental data related to precipitation and actually how do you get data from these films. So it's really important when we're studying wetlands that we think about the normality of our rainfall. So here we have the kind of pink dots are my sites and the stars are rainfall data sources that are kind of generally grouped in where my sites were. And I'm going to give you an example of one of the regions kind of precipitation analysis we did. So these two graphs are monthly precipitation data in inches, as well as some more historical WETS data. And basically, my time period is, for my study, is in these green boxes. And what these lines represent, so we have the yellow line, that represents the average monthly rainfall data. The gray represents the 3-month weighted average. The orange on the horizontal orangish one on the top, that's the 70th percentile, and the blue at the bottom is the 30th percentile. Basically, what this means is that when your monthly rainfall data, the gray or the yellow falls within those two horizontalish lines, you're in a normal rainfall year. But you can see that my data, that it kind of is on the drier side of normal or below that 30%. So meaning it was a drier than normal year during some parts of the study. Additionally, we had our water table data. This is a hydrograph of 4 of the sites in this region. And you can see that as we move into May, we just dry out completely, essentially. So another way to kind of talk about this saturation data is based off of the Hydric Soil Technical Standard hydrology requirement. So if you're using the IRIS films, you also have to meet this requirement to count as a wetland soil. So the water table has to be within 25 centimeters of the surface for at least 14 consecutive days, so 2 weeks straight. And the way that this graph is set up is I had my 11 different sites, and I'm just showing kind of like a histogram of, for each batch, how many of those sites made that requirement. As you can see, even in the beginning, only maybe half of them met. And then as we continue on into the 7th batch, none of them met. And there were some sites that never met at all during any of the batches. That just kind of showcases the dryness of the season. Okay, IRIS films. So I mentioned something about thresholds earlier. So when we're looking at IRIS films, we have to meet a certain percentage of removal. And the way that the technical standard has that laid out for the iron is you have to have a 15 centimeter contiguous zone in the upper 30 centimeters of your film that has 30% removal or more in the majority of films, 3 out of 5. I know it's a lot of verbiage. I'm going to visually show this in a minute. The manganese doesn't have an approved threshold because it's not approved by a technical standard, but Rabenhorst and his colleagues proposed that basically use the same threshold with the caveat that you only use it in the cool soil conditions. So what does that actually mean? So this is a batch of 5 films from one of my sites, and we cleaned it up, scanned the image, and what we do is we represent this white area of removal. We actually convert it into a binary image and convert it black into Photoshop. And once we have this image, we put it through MATLAB, and for every centimeter down the film, we calculate what percentage of these areas is now black pixels. And we can tabulate all that data and present it into a graph like this. So this graph shows on the x-axis the percentage of the paint removed, and then on the y-axis, it's the depth. So the top is the soil surface at 0 and decreases with depth. So these different lines are all the individual films and the percentage removal for every little centimeter going down the film. And this red dotted line represents that 30% threshold for the iron. So I mentioned we have to look at a 15 centimeter zone. So that's what we do. We look at every 15 centimeter zone down to 30%, and we can again graph that again. But this time we want to look at where is the maximum amount of removal, like which 15 centimeter zone has the most removal. And for us, that's right at the bottom. We have 3 of our films that are above 30%, 2 that are below. This means that we meet that hydric soil requirement for the technical standard for IRIS films. So again, we're only looking above this red line, 30 centimeters up. We found that the 15 to 30 centimeter zone had the most removal. We calculated what that removal was. We had the 3 films, and with 39 being the median value of removal for this whole set. So that's how we think about iris data. That's how we get it. So talked about precipitation, talked about iris, and how we get the data. Okay, what does the data show? So we know based off thermodynamics that manganese is reduced easier than iron. And when we just did this very simple scatter plot of iron removal on the X versus manganese removal on the Y, we see this relationship where about 2 to 3 times as much manganese is removed off their films as the iron is. We do see it plateau a little bit, but that's just because as you keep increasing the iron removal, you're basically already maxing out the amount of manganese that can be removed. Okay, nitty gritty. So first, we're going to talk about temperature and saturation. And all of these box plots represent cool data. And this cool data, again, is below 11 degrees C. Why 11 degrees C? That's based off of the previous work done in the natural wetlands. So these box plots represents the mean removal for, in the orange, that's the iron, the brown is the manganese, and then these are outlier box plots, so the whiskers represent the 1.5 times interquartile range, and then we have the 75th, the median in the middle, and then the 25th percentile represented in the box. So we have a series of graphs. These graphs represent different amounts of saturation. So 0 days of saturation, so dry, and 21 days of saturation, more very, very wet, for the deployment period of 28 days. I want to look at this data in a more targeted way though. So we have the 30% line highlighted here in the red. And if we look at the manganese brown boxes first, we can see that the median values of the removal are well above 30% once we have a sufficient amount of saturation, and it basically increases with more saturation. Of course, there's some variability, but the bulk of the data is much higher than 30%. But when we look at iron, the orange boxes, we see that the median value is below that 30%. The bulk of the data does not reach that 30% threshold that is established by the technical committee. So this illustrates the issue of that in the cool conditions, there is some suppression of iron reduction. Now flipping to warm, so same exact setup, but now this is all the warm data. When we look at manganese, we see, again, kind of the same relationship and even more removal with the increase in saturation. However, it's overly sensitive. We only have maybe a couple days of saturation, and it's way above 30, the bulk of the data. So that's an issue. It's overly sensitive, and this is why we don't want to use them in these warm conditions. But the iron, finally, the bulk of the data is more than 30% when we're in these very saturated conditions. We're meeting that 14 days or more saturation requirement. But we're not seeing that so much in the drier conditions. Of course, there's variation, but the bulk of the data shows what we want to see. Additionally to saturation and temperature, we wanted to look at organic carbon. So this is one way we looked at organic carbon. So this data is a little different in the sense that all the data points here are wet, so they met that 14 days of consecutive saturation. And we have the left two is like low carbon status, and the right two, the soils were a higher carbon status. We grouped them this way because we sampled for organic carbon based off horizon, and all horizons in the soils are different depths, so it made it a little difficult to look at the actual like continuous numbers. So we just decided to group them into these two levels. But overall, we can see that with the higher carbon, there is more removal occurring than in the lower carbon. And for example, the manganese, the variation shrinks a bit too. This is not as data-driven, but more anecdotal, but we can also see, for example, in this profile that has a lot of organic carbon at the top, this is an example of where they brought in organic rich topsoil and added on top of a very cut down profile. And we can see that the removal, the white spots on both of these films are centered around that organic rich topsoil zone. these different drivers that I'm talking about, the saturation, the temperature, the organic carbon, they're all significant, and this wasn't really too surprising, but it's good to see. And there is also lots of significant interactions between these different drivers. Now, still on iris, but we're going to shift gears a little bit to thresholds. And so, is that 30% threshold that the technical standard has, is that really the best threshold? So we wanted to explore this idea with these different figures. And I know that's a lot, so we're going to simplify it first. So these graphs represent cool data. The left side is iron data, the right side is manganese data. And the way that this works is these x-axes represent potential thresholds. So for example, the current is 30%, but what if we shifted that 30% to like 70 or 10? How do the data fall out into these various groupings, which I'll explain right now. So this blue zone represents wet and reducing outcomes. So this means the soil is meeting that 14-day saturation and we're meeting whatever threshold. So for example, we're 30% removal or more. So this is good. This is showing what we want to capture. It's wet and reducing. So good. Gray is the opposite. It's not meeting that saturation requirement, so it's dry, and we don't have enough removal based off, for example, the 30% threshold. So it's not reducing. So that's another desirable outcome. We're not capturing, we don't want to capture dry sites. However, green and orange, that's where things get a little problematic. So green is where we're meeting that saturation requirement of the 14 days, but we're not reaching, for example, 30% removal. So for some reason, we're not capturing the anaerobic conditions, even though it is very clearly wet, often the case. So that's an issue. Orange is a similar but opposite issue. So we have too much removal. We have 30% or more removal, for example, but we don't have the 14 days of saturation. It's too dry. So this is giving us a false positive result on our iris films. So when we're looking at these thresholds, we want to minimize the area of the green and the orange proportions. So when we are thinking about the cold iron data, the 30%, we see an issue. About 30% of the data that falls into that green zone, meaning they're wet, but we're not accurately capturing that they're also anaerobic. So we are suggesting that we lower the really high conservative value of 30% to 15 in cold conditions, because we're able to minimize the majority of our problematic issues. Now, when we jump over to the right side for the manganese, we see that 30 actually is a pretty good number here. It's maybe not perfect, but it's a good representation. It also fits well with our previous knowledge and what Dr. Ravenhorst and his colleagues found in the natural wetlands. Now, when we look at warm data, things change a little bit. So the bottom left is the iron when it's warm. We think 30, the original 30 is really probably the best bet here. Now, there's a lot of this orange, and I think that's mainly due to my smaller data set and also due to kind of the flashy water tables that occur at this site. But there's a lot of years of data and research that support the 30% threshold removal across the country. So we think this is still the best bet for when iron iris is used in warmer soil conditions. But for manganese, it's not good for interpretation. I mean, you could put them out there, but they're gonna be overly sensitive. You're gonna have high amounts of removal even when you don't have that much wetness. So they shouldn't be used in these warm soil conditions. So overall, there are significant differences in how the manganese and the iron iris removal occurs, with the manganese reduction being a lot more sensitive to our specific environmental drivers we looked at, which was saturation, soil temperature, and soil organic carbon. These are significant drivers for the iron and manganese reduction and removal. The study supports that we could create thresholds that are, one, temperature dependent, and two, can benefit us using them in this early growing season condition, with the cool being 30% for the manganese, and instead of 30% for iron, we need to bump that down to 15. And then for warm, we're not going to use the manganese. It's just not going to be very useful. But the iron, we should use the same 30% removal threshold that we've been using. I said I would do a quick sneak peek of my other project. So I'm not going to explain a ton about it, but basically we wanted to look at almost all the same things that we did in my field study, in the lab, and under a more controlled setting. So we set up these microcosms where we had 3 different soils that are common to the mid-Atlantic, and we looked at the effect, again, of temperature, organic carbon, and saturation. We did this by having a setup both in the lab upstairs, which is representing a pretty warm soil temperature, and then also in the walk-in fridge in HJP, which represents really, really cold soil temperature, but it's a little extreme, but it works. And organic carbon, we looked at different different horizons in the profiles, so we got a natural distribution of different levels of organic carbon. And then saturation, we had these basins, and we had different time points in which we destructively sampled to look at the amount of reduced and mobilized manganese and iron in the actual pore water. So we collected that and ran that on the atomic absorption spectrometer. But then also we had fun little mini iris films within the tubes. So we were able to kind of look at that in correspondence with our pore water data. Another thing we got to do that we didn't get to do in the field study was looked at the impact of how much manganese oxides are in the system, and if that at all impacts when and the rate of the iron reduction. And because the manganese is thermodynamically easier to reduce, and that generally reduces first in our ideal model, we thought maybe you would have a kind of, it would suppress the iron reduction, or at least make it delay the reaction. And guess what? That's what we saw. So cool. But without further ado, I'd like to thank you for listening to my presentation, and shout out to Dr. Gallo's lab for letting me borrow a camera. We had a pesky creature biting at our iris films, and looks like this coyote was caught red-handed. Yeah, so, but I'm gonna leave us with this conclusion slide and open the floor for questions. Thank you. Yes, hi Sarah.
That was great. I just have a clarifying question.
Sure, yeah.
To start you off. The paint was around like 360 degrees around the tube.
Okay, yeah, this is where I wish I brought my props. So, so the films, they're flat sheets, but the way that we install them is we have something called a delivery tube. So we put them inside this like other clear PVC tube, and we basically insert it into the ground and leave the film behind. So it's in this kind of tube-like cylinder-like shape, but you can flatten it out and scan it. The original iris devices were these big PVC tubes that were painted on, but there was lots of issues with them getting scratched, or just they're taking up a lot of space. And the biggest issue was actually trying to get an image from a 3D, like they had, Dr. Ravenhorst's group was quite innovative and created this like scanning, rolling kind of system, and I'm glad I didn't have to deal with it. So the films really allow us to get a much crisper image. Yeah. Yeah. Hey, what's up?
Great job.
Thanks.
Did you do any analysis comparing like the more manufactured soils versus like
Oh yeah, because I mentioned there was a bit of a difference. So I haven't actually done that yet. I had thought about it, but then I got kind of lost in my other project. But it would be interesting to see. It might be a little difficult to like truly separate that out, because I will say the historical records for the restoration of these sites was a little spotty. But might not be bad to look at for my thesis, so I'll keep that in mind. Yeah, it would be interesting if anything comes up. Yeah, hey. Sorry, yeah.
Okay, great presentation, Grace.
Thanks.
This is a really fascinating study. How would you define wetland? Because I know that.
How would I define wetlands?
Yeah. What I've heard is that it's often like sort of debated upon.
Yeah, I mean, there's definitely different types of wetlands,
Okay.
and so I think that maybe
It's too broad.
goes into that, but I think that whole definition of you have to have the wetland plants, the wetland hydrology, and the wetland soils, which I know sounds kind of like circular in a way, but I think that really is what distinguishes the plant communities. The soils are completely different. Being in that saturated condition just completely changes the chemistry of the soils and what plants can grow in them, and then of course you need that wetness. So I think it's really all stems from that wetness, hence wetland, right? But when you go into the specifics of like what types of wetlands and things like that, one, I'm probably not the best person to actually ask about that, maybe if Dr. Baldwin's not here. But I don't think there's much debate about that three-prong definition, though. Yeah.
Thank you.
Hey, Daniel.
I see that I saw evidence that the manganese ions didn't form that well at warmer temperatures.
Right.
That it was overly sensitive.
Right.
Was there any evidence that you came across in your study that it might, like its use might be beneficial or it might have some advantage in some case out there?
In a warmer condition, you're talking about? Like, yeah. So, I mean, of course, our argument is that maybe in this cooler condition, it's more useful. But in the warmer condition, I think it still can be useful, especially when you're maybe that like first year of restoration. The soils are maybe just not really reducing that much. Like the the actual redox potential of it might have not established quite yet. So it might be at these kind of a zone that's more prone for manganese reduction. But the other thing I would think of is the other reason why people are interested in the reduction of manganese is because it's at a similar level, as I said earlier, as like denitrification. And a lot of people are interested in that process, and people even create wetlands just for denitrification as a service. So maybe that can be used as a proxy. I don't think anyone has actually published any research yet, like showing and establishing how you can use the manganese films to look at denitrification. But I know there's a lot of interest in doing so. So that might be a way to use them also in warmer conditions. Yeah. Okay, good question. Yeah, hi.
Do you think it's possible that the distance that your like water data, I guess, like the rainfall data that you got
Sure.
may leave room for error?
Yeah, absolutely. I mean, I didn't have like rainfall data at every single site, of course. So there is obviously variability. Some of the rainfall stations were a bit farther from my sites than others. So there could be, but I think overall as a regional basis, I don't think there's a ton of like room for error when it comes to that. But, you know, of course, everyone wants the most accurate, most pointed data to your research. So there could have been a little bit, yeah. Did that answer your question? Yeah, okay, great. Okay. Hi, yeah.
So it looks like, so you have these nice recommendations of manganese and iron, paint removal thresholds, temperatures that you got from your data.
Right,
From these restored sites.
right.
Do you think that would apply to all wetland sites that use these thresholds, or would you apply that to
Sure.
specifically restored sites?
If my data was alone, maybe it would be better to say just restored sites, but because this is kind of a spin-off project based off the research that Dr. Ravenhorst and his colleagues did in natural wetlands, and they did this in 8 different states. A lot of the states were in the mid-Atlantic, but there was some in, let me think, Nebraska, Wyoming. We were in other regions as well, or not me, they were in other regions as well. So I don't know if there were how many different types of wetlands there were, but I think they saw very similar results. I think the 15% threshold maybe was a slightly different number, but in the same range. And then the 30% for the manganese was the same recommendation. So the fact that we saw it also in my restored wetlands, I think just strengthens the idea of it being in these natural wetlands. If you want to comment. Dr.
So the iron 30% threshold seemed pretty solid. The natural wetlands, we actually probably would have pushed that number down lower than 15%, down to like 5 or 10%.
Right.
Based on the natural wetland settings. But still, it should be definitely lower
Than the 30.
than where it currently is if you're going to look at it in
cool part of the growing season.
And I guess like, let me see. I don't know if I should get into this too much, but these iris films, these mini ones are showing like, this is a topsoil egg horizon with a lot of organic matter, and then we're going down in our profile depth. But I just want to show you that the brown is like completely removed by the time we're reaching even 28 days, and there's still presence of the iron. So this is in the warm conditions. But if we were to show you this in the cool conditions, there is just barely any removal of the iron. So that's just kind of showcasing that cold temperature is really like suppressing the iron reduction. And that's why in the natural wetlands, they found an even lower threshold than the 15, but mine is somewhere around 15. Hopefully that wasn't more confusing. Any other questions or comments? Hi, Patrick. Yeah.
As you said, restored wetlands are often added with organic matter.
Yeah.
And that slide you showed with the picture of the egg horizon and the iris film showing a significant amount of removal.
Yep. We're almost there.
That's pretty interesting. Do
Yep.
you think maybe something should be done to like compensate for the addition of organic matter, or the organic matter is somehow like not being representative of like the true hydrology and kind of like speeding up the reduction of iron and manganese? That makes sense.
No, it makes sense. I'm trying to think of an answer. Or at least a thought. So I guess in this particular profile, it's interesting because we do have saturation, if I remember correctly, almost all the way to the surface of these films. It's more the fact that we're not seeing the reduction in these lower parts, except for, that's probably actually more scratches if anything. But in this like BT horizon where there's only like 0.25%, we're seeing maybe like little splotches. But I think that's maybe more of showing the issue with wetland restorations actually, because to give a little bit more context to this profile, it was excavated down multiple feet to get the surface of the wetland closer to the water table level. So they removed any of the original like kind of topsoil that was there. And so we're cutting very deep into this subsoil, and then we're adding this organic rich. So there's not really there's a little bit of a transition in that second horizon, but I think it's more of the case that we don't have this natural setup of where you have a natural accumulation of organic matter over years and years of saturation and plants senescing and becoming part of the soil system. So I don't know if that really answered your question, but that was just my whirlwind of thoughts based off your question. Anyways, we can talk about it more.
But just to follow up on that.
Sure.
So like you are selecting though like you're trying to figure out like a general depth threshold from which to use to like make your assessments, right? And
Well, we always look at 30%, the top 30, or not top 30%, the top 30 centimeters of the soil. So
one way, like, based on what Patrick was saying, like one way to correct for, or if for some reason you wanted to like ignore this, you could, I mean, would it make sense to just ignore it, to like cut off like the top part of the data and just focus on
I mean, for me, it doesn't really make sense because it's there.
Right.
And it means something. And also I think it just showcases like if this system has time to develop and more organic carbon begins to accumulate, eventually we'll start seeing it maybe either growing in the topsoil, or maybe there'll be some sort of minor translocation into the subsoil, unlikely. But I think it's just more of kind of showing the potential at this site is if there's the carbon there, it is acting like a wetland soil, at least in that top zone. So I guess that's more of what I would think about this particular site, because this is, This one's a site that actually drains into like a wooden wetland area, but we were outside of that wooded area. We were kind of chose a more kind of marginal area, kind of maybe potentially closer to the wetland edge, so that could have also contributed. But if I remember correctly, this site has only had maybe at most like eight years, or actually maybe 5 years. So it just hasn't had a lot of time to establish. But I don't think cutting it out would make sense. Yeah, that was a long answer for that question. Sorry. Are we done? Are you cutting me off? Pull me off the stage. Okay, thank you.